And I am recording.
All right.
Let's do this thing.
I guess I'll stay in this meeting. So today we're going to talk about optimization. Mr. Kirk, what are things that are nice to optimize?
What are things that are nice to optimize? Things that have maximums.
Mm-hmm.
Because like not everything has a maximum. Some graphs, some phenomena, they increase or decrease without bound. Well, maybe not. The expansion of the universe.
Okay. Yeah, that would be
I think one thing
difficult
that's
to measure.
Yeah, but measurable. Hopefully one day our students are doing that. That's what we're here for. One thing that I know is really easy to easy is the wrong word. One thing that is maximizable or minimizable is a quadratic. There's one max in a quadratic equation, a parabola.
Mm-hmm. If it's a downward facing parabola, right? But if it's an upward facing parabola,
or a min if it's an upward facing one, right? Mm-hmm. Sometimes we want to minimize things, cost.
Mm-hmm. Losing, we want to minimize losing.
Want to minimize losing, maximize winning. Can we create a word problem that involves winning?
Like the University of Maryland.
The University of Maryland, 1 and 1, 1 and 1.
Which is, not terrible.
No, it's not a maximum. We are on that trajectory. There you go. That's what I got.
All right.
That's my take on optimization.
I think optimization is one of the more useful things in math in terms of like applied math, because like what are businesses interested in? What are governments interested in? What is anyone funding research really interested in? Is maximizing the benefit and minimizing the risk, or minimizing, negative outcomes for things like, you want to minimize side effects for drugs. You want to maximize like the benefit of doing things. It's just optimization is so useful. And if I
have an anecdote. Can I share it? I was at a robotics competition, and a parent came up to me and said, I think that schools need to teach more optimization. And I'm like, well, let me tell you that I teach optimization. So this is something that people want, businesses want, companies want, and you're getting it. We're going to do some optimization.
And it's not terribly complicated either, which is also a really nice thing. Like many of the steps that we're doing are really intuitive. The problem really is how to set up the problem, because solving the actual problem is not terrible. So let's try it. Mr. Kurt, can you read that first question for us?
Yeah. All right. So we got find the quadratic equation that has the indicated vertex, 3, 5, and whose graph passes through the given point, -1, 8.
Okay. So how do you think we should start?
We've been talking about quadratics for a little bit. Mm-hmm. We have different forms. Can we write those forms down?
Yeah, sure.
We have vertex form. I'm feeling that might be useful here.
Mm-hmm. Because we're given a vertex.
Mm-hmm.
All right. What other forms do we have?
We have standard form. That's ax squared plus bx plus c. Take advantage of the quadratic formula with that one. You also get the y-intercept with that one. And then we have factored form.
I spaced that poorly. But yes, we have factored form where we have like 0 is something. Oh, my eraser does work. Wild.
Nice.
Okay. X minus R1 times x minus R2. Okay. Yeah.
Sweet.
So for this quadratic equation that we're looking for with the vertex that's given, and we're looking to pass through a point, you were saying that we should try vertex form. So vertex form is what is that? F of x.
F of x a, right?
And then x minus
h.
Something. H. Sounds good. And then squared.
Our quadratic plus k.
Plus k. All right. And we're not using b and c because it's just we'll get bogged down by notation, and we don't want to deal with that.
Mm-hmm.
Okay. So our
H and K is there because it's the vertex, right?
Yeah.
Let's squeeze a 3 and a 5 in there. Let's rewrite that thing with 3 and a 5 instead.
So we got a times x minus 3 squared plus 5. Cool. So now I have only 3 unknowns in my equation. What should we do now?
Well, we have a point that gives us 2 more of those unknowns.
Oh, okay. So
because
this is
negative
our
1,
x.
8 is xy. Or we're not using y here, f of x, function notation.
So we have an 8 equals a times x. Oh, wait, no, we have an x. The x is negative 1 plus or minus 3 squared plus 5. Okay. And that's also really not terrible, right? We can handle that very nicely.
Mm-hmm. Let's do it.
Let's do it. I'm going to draw a line so that we have a little
Smart.
bit of space. So 8 minus 5, 3 equals a times negative 1 minus 3 is negative 4. Quantity squared is 16. So then we've got to divide by 16. We got a equals 3/16. So now in our vertex, we can write our quadratic equation in vertex form, just substituting in what we know. And I'm going to change colors. So we have f of x.
Go Terps.
Go Terps.
I'm going to try to squeeze in Go Terps as many times in this video lesson as possible.
Oh,
Go Terps.
Fantastic. F of x equals, go Terps, 3/16 times x minus 3 squared plus 5. And that is our quadratic equation in vertex form. And that's totally okay because that is one of our forms that we were talking about.
What do we say when we get the answer?
Go Terps.
Go Terps.
All right. So that's not too bad.
If given vertex and point, vertex form is the way to go.
And vertex is just a special point, right? Which gives us a little bit more information because then we can plug it straight into vertex form. So what if we're just given 3 points?
All right. Just given 3 points. Now, I'm thinking about the 3 forms we have. We have vertex form. And I mean, maybe we've been given a vertex, but that's not apparent.
Mm-hmm.
Standard form, we could do that. We could plug stuff in and get 3 equations, 3 unknowns, solve it. But 4, 0 and 8, 0.
Those are roots.
Yeah, that's when the graph crosses the x-axis.
Lovely.
Right? X-axis, not y-axis, right? 4, 0, 8, 0. The y is 0. X-axis intercepts. Boom.
And then we also have some point. So we got some point
boom.
10, like 36 up there. So we're probably going to have
that point's high up.
Yeah, it's really up there. So we're going to probably have something kind of like that.
Boom. And I definitely up, right? I think we can use the fact that that point on the outside of 4 and 8 is above 4 and 8.
Mm-hmm.
Well, this must be an open, an upward opening parabola.
Parabola. Okay, so in our, so can we leverage our factored form for this?
I think so. Now I know that there's many different functions that have the roots 4 and 8.
Mm-hmm.
So we're going to have a dilated factor probably.
Mm-hmm. So we have some dilation happening with our a, the vertical dilation happening with our multiplication by a. And then we have R1, x minus R2, and this is going to equal like our, well, we can use y, right?
Why not?
Why not? Go Terps.
Go Terps.
We have, and then we also have a point 1036, so we can plug in for our x and our y value, right? So we have 36 equals a times 10 minus, and what's R1? Does it matter?
Is it 4 or negative 4?
Is it 4 or negative 4?
So 4, 0 is the coordinate. What is the root? Just like
the negative of our coordinate.
Right?
Yeah. So then we have what?
Minus 4.
Minus 4 times 10 minus
8
8. All right.
Money.
So that's a bunch of multiplication. We can handle that. 36 equals A times 10 minus 4 is 6.
6.
10 minus 8 is
2.
2. And then, we can just like divide out by 12.
Yeah, or divide by 6 and 2 at the same time.
Or we could factor. 36 is 6 times 3 times 2.
I like that. That's snazzy.
Zoom, zoom,
Go
zoom,
Terps. Go Terps. Go Terps.
And A equals
No lightsaber
3.
noises today.
Oh, it's only go Terps.
Yeah, just go Terps.
All right, that's fair.
Every cancel is a go Terps. All right.
Equals 3 times x minus 4 times x minus 8.
Oh.
And does this like final format, does that match our rough sketch of what we were thinking about over here?
We got a root of 4, root of 8, and then I guess we can just double check when I plug in 10, do I get 36? I mean, I guess based on our algebra, we're totally going to get it. We're going to be doing algebra in the backwards way. 6 times 2 is 12 times 3 is 36. Yeah, so this is going through those 3 points.
Cool. And so we throw a box around our answer and then we say,
go Terps. I really hope that no one despises the Terps. I mean, why would you?
You can't.
Great institution.
Yeah. And plus, like, I don't know, there's the University of Maryland. Like, we're a school in Maryland. We have
UMDA.
We have to.
Yeah, don't like root for these other schools like Duke and UNC.
Or like Rutgers.
Rutgers.
Northwestern.
Jersey.
Boo, New Jersey. Okay, so
Boo, New Jersey. Uh-oh.
So for this third one, well, that doesn't look quite as nice, right? Because the points that we were given before, we were given roots, and that was lovely. We could just like use our factored form and then do a little bit of work, and we will get our equation for our quadratic function. But now we just have 3 miscellaneous points that are not zeros for anything. We're not told that they're vertices. So what do you think we should do?
Well, scroll down for me. These 3 points. The first thing I want to think about is what you're saying. But after I've declared that I don't have roots and I don't have a vertex, are any of my points like the same level? Why?
No.
No, because if they were, then I'd have some symmetry.
Oh.
I don't know how that might help me, but I just want to throw that idea out there. Let it like marinate. If I have 2 points that have the same y value and they're not roots, I still have the same y value. I can take advantage of some symmetry. We don't have that though. The only other form I know is standard form. I think we just got to do it. I think it's time.
Standard form.
Yeah.
Wait, I need to do like a really bad sketch of you. This is you thinking about symmetry.
I'm gonna. Oh, are you giving me the hat?
Yep.
Nice. Here, I'll pose so you can use me as a.
Oh, okay. I don't know if I can do the hand, but I'm just doing the beard. That looks really bad.
That looks like a pig.
A pig?
That looks like the pig nose.
Pig nose? Where's the nose?
Let me I can steal right there.
Oh, that's your eyes.
Oh, all right. I can see that. All right.
All right. So, standard form where we have ax squared plus bx plus c. We didn't have enough coffee today. I think that's what happened.
I only have 1 cup.
Yeah, me too. Okay. So this is equal to our function, or we could also call this y. Let's call it y because I'm feeling slightly lazy.
Can you do something for me?
No.
Can you put the... Oh, fine. I was going to say, can you put the y on the other side?
Yeah, I can do that.
Yes!
I felt that question coming.
You can hear it coming.
All right, so we'll just plug it in. So we have y values. We have 3 equals a times 1 squared, which is just 1,
Just 1.
plus b
Oh,
times
this is going to be great.
1 plus c. Oh, that's nice.
That's like some Sesame Street stuff right there. ABC.
ABC. Nice.
Apki Defki Jugamanoff Kerstuvixes is how Big Bird says the word A, B, C, D, E, F, G.
Yes. Also known as the alphabet. So we have...
It's my favorite episode of Sesame Street.
Is it? Wow.
Yeah.
I don't think I have a favorite episode of Sesame Street.
I mean, once again, I said last time, my favorite is fluid. My favorites go up and down and changes all the time. But currently, in this moment in time, my favorite episode of Sesame Street is the episode where Big Bird discovers the alphabet.
So I'm just substituting in here while we're talking about Sesame Street. So we have 45 is a y value, and then we're plugging in 8. So 8 squared, that's what, like 64a plus 8b plus c. All right. Well, we have 3 equations and 3 unknowns. So what do you think we should do, Mr. Kirk?
I think we should start using whatever your favorite version of solving system of equations is. Mine is equation subtraction.
Equation subtraction. That's
our goal, I think, is to eliminate variables. Hopefully, everyone remembers this from algebra. But if not, you're going to get a level 3 example here. 3 equations, 3 unknowns. Can we subtract the first 2 equations?
Sure. So
I think that's going to get rid of the C.
So we're taking these 2 equations, and we're subtracting, let's go top minus bottom, right?
Big fan of that, yes.
So we have...
keeping it positive.
3 minus 5? Oh, you want to go... Oh, you want to go bottom
top minus bottom? No, bottom minus top. You got to keep that...
fun.
Keep things... Are you negative?
No, but I think everyone just needs to be okay with working with negatives.
But when given the option, I think it's reasonable to choose positive over negative.
That's fair. So
just
5
like when we
3
restrict functions so that their domain is 1-to-1, we often resort to the positive if necessary.
So we're going bottom minus top then. So we have 5 minus 3 is 2. 9a minus a is 8a. 3b minus b is... Oh, wait. Can you see my cursor?
I cannot see your cursor.
All right. Well,
you're experiencing my issue.
I forgot about that. So then, and then we have c minus c, which is 0. And so I'm just going to erase that so we don't have to deal with it. And look, we simplified it just a tad. That's nice.
All right, we have an equation with 2 unknowns. Unsolvable. Can we get another equation with 2 unknowns? Can we subtract the bottom 2 equations to get a second set of equations, hopefully eliminating C again?
Okay.
I think it's going to disappear as well, yeah.
So we want to do like bottom?
Yeah, bottom minus middle.
So we should change this to
You change the B to an M, yeah. Middle minus top, bottom minus middle.
Bottom minus middle.
But I think we could do bottom minus top if we wanted. We could do... We I like bottom minus middle, though.
Yeah, bottom minus middle. So 45 minus 5 is 40. 64a minus 9a. 55a. 8b minus 3b. 5b.
Oh, you know what I'm thinking?
C minus c. Should we divide?
Can we just scale both of these equations down by... can we factor out of each of these terms in our first equation and our second equation the greatest common factor?
Heck yeah. So the greatest common factor in the middle minus top is 2. So we got 1 equals 4a plus b. And our greatest common factor in our bottom minus middle is 5. So we get 8. Let's scroll sideways a little bit. That's only a little bit helpful. Is 11a plus b.
And now we got b's. Buzz, buzz.
So we're going to try to take these and combine them.
Not the murder hornets.
Not the murder hornets. I saw a cicada killer wasp, and it was terrifying.
Did you know the 17-year cicada is next year?
Yep.
I'm so excited.
Yep.
I remember being a little kid and being like, there are so many cicadas.
Well, I had to walk to school when the cicadas were happening, and it was like so smelly.
Crunchy, crunchy. Crunchy, crunchy. We used to hop on them at the bus stop. This is. We're gonna get yelled at by PETA.
Yeah.
Let's keep going.
Don't approve of smashing cicadas. Although if you want to learn more about bugs, take Ento.
Yeah.
Okay, so let's go. Let's keep it positive. So 8 minus 1
Keep it
is
positive.
7.
Sorry.
11a
my
minus
life.
4a, 7a. And b minus b is 0. So a is 1.
Boom.
Great. We found a. Now what do we do?
Backs up.
Back sub. So should we use this equation?
I think we should inspect all of our equations and choose the best one. And I like the one you underlined. Yeah.
All right, cool.
I didn't see the underline.
So we have 1 equals 4 times 1 plus b. And so that gives us 1 is 4 plus b, and b equals -3.
Let's use the bottom equation to get C. Just
Bottom
kidding.
equation.
We
This
got
one?
him. Let's do
Are
the
you
first
sure?
one.
We can.
No, let's do the top one. Top.
Okay, yeah. Don't be afraid of computation, Mr. Kurt.
I ain't afraid. I just look for opportunity.
Oh, wow. It's almost profound. 3 equals.
Almost wise.
I need more coffee. Plus C. Okay, so I substituted in the A and the B that I had from before. 3 equals -2 plus C, so then 5 equals C. Great, I found A, B, and C. Am I done?
Yes, because all we wanted was some letters.
Yeah. All right, let's move on.
No. Plug it back in. It said find the quadratic equation. One of my biggest pet peeves when people don't. Well, they read the question. They understand the question. They solve the problem, but they don't like reread the question at the end to make sure they answered it. Let's make sure we answered this thing. Find the quadratic equation that passes through the points.
So we have an equation. We're starting an equation, and we have A is 1, so we don't have to write that. B is -3, so we have -3x, and then plus C is 5.
Boom.
And there we go. Go Terps.
Cool. Go Terps.
So that was nice, right? So the things that we did, we used actually all of our different forms of quadratic equations, depending on what we were given.
Mm-hmm.
And we leveraged things that we knew. So if we knew that it was a vertex, then we used vertex form. If we were given some roots, then we used the factored form. If we weren't given any of that helpful information, then we did a lot of work, but it wasn't terrible. And we kept track of our variables. We kept track of labeling things in a way that made sense. And then we read our question and got an actual answer.
And all the while, we respected the Terps.
Go Terps.
Go Terps.
So now, what is the greatest product of two positive real numbers whose sum is 110? That feels like not related at all to anything we've done before. What do you think, Mr. Card?
Product. I'm thinking multiplying stuff.
Multiply. Okay.
Stroll up. I'm looking at these. Scroll further. I'm looking at these 3 examples, 1, 2, and 3, and I'm thinking, do I have multiplication happening in any of these? Number 2 is some multiplication going on.
With the factor form?
Yeah, with factor form. I'm just thinking out loud, like we're finding the product of 2 things. Number 2, there's products going on. I don't know. Let's head on back down. Bring it on back to number 4ville.
Number 4ville.
That was a SNL reference. Justin Timberlake. Bring it on down to Baskerville. No?
Sorry.
Right. That's okay.
I know about the fly.
Anyways. What is the greatest product of 2 positive real numbers whose sum is 110?
So should we set up like variables for our 2 positive real numbers?
Mm-hmm.
So what variables do we want to use?
L and I was just trying to be obnoxious. I was trying to pick the most obnoxious letters, but let's go with L and M.
And M. Okay.
Why I chose those? Just feeling them.
Okay, that sounds good. So we have 2 positive real numbers that we're defining as L and M. So L and M are in the set of positive reals. And we need their sum to be 110. So L plus M needs to equal 110. And this, I would like to call this something, I would like to call it a constraint.
I feel like I'm being constrained by that equation.
Well, you are, because this is pretty much the only information that you're given in the problem of like what we're allowed to use. So we have L plus M equals 110, and we also know that L and M have to be greater than or equal to 0, or greater than 0, strictly greater than, right? Because they're positive. And we're looking for the greatest product of these two numbers. So we're looking at L times M using the multiplication that you gave us, but I'm going to erase that dot. So we have L times M, and we need to maximize this. So we want this to be the greatest number possible. And we want to maximize their product. So P for product, right? So P is product. And this is what we're trying to maximize.
All right.
And we're going to call this an objective function, because our objective is to maximize the product, which is P. Okay, right. But now we have two variables, which is very upsetting because we don't yet understand how to work with multiple variables yet. But that will come eventually in further math studies. So how can we leverage our constraint to make our objective function better?
All right. Well, we have a relationship between L and M that has been given to us. L plus M is 110. Can I somehow do what we did before, eliminate a variable from this product?
So perhaps like choose a variable that we want to solve for and then substitute that into our objective function?
Let's solve for M, because go Terps.
Okay. But then we won't be working with M. We should solve for L if we want to use M.
You're right. Let's solve for L, so we're working with M.
Solve for L. So L equals, when we subtract M from both sides, we get 110 minus M equals L. So now in our objective function, we have the product is 110 minus M times M. That's our objective function. That's what we're trying to find the maximum of.
That's a quadratic.
That's a quadratic. Wild. Should we
that's the root?
M?
I don't want to. We're in that root form.
Oh yeah, we have
from number 2.
Form. Yeah.
I think we can let's graph this real quick.
Okay.
Oh, you're thinking like me, cool. Let's graph this and then try to figure out what the maximum is.
Where's the other root? Is it a positive or negative 110?
I want to know when the graph is 0.
Okay.
So what do I need to plug into this equation to make it 0? To make it
so.
Well, 0 does that. You plugged in that 0. 110 minus 0 times 0 is 0. But I want that other term, 110 minus M, to be 0. So I think 110 is our other.
Positive 110.
Yeah, positive 110.
Fantastic. And just to get an idea, a better sketch, because now we have 2 points. What kind of parabola is this? Is it opening upward or opening downward?
Well, I know that the coefficient of my standard form, the leading coefficient of my standard form, ax squared plus bx plus c, whatever a is, if it's positive, it's opening up. If it's negative, it's opening down. And I think just expanding this in my head, we're going to get a negative m squared.
So we got opening down.
Yeah.
All right. And that's a really bad sketch, but that's okay because it's a sketch.
Well, the only thing that bothers me is if this goes through at 0, then it should be in the 3rd quadrant after 0.
I think I did that. I think I just
I thought that the y-axis was the curve.
Yep.
I'm sorry.
It's not a function.
I'm sorry. Not a function.
So just like intuitively from this, what do we think? Like, where are we going to estimate our maximum is going to be?
Symmetry.
Parabolas,
yeah. Halfway right between.
Symmetric. Yeah, halfway between our roots, right?
Yeah.
So what's half of 110?
55.
55. Okay. Cool.
And if it wasn't 0 and 110, I would just add them and divide by 2.
Oh, add the roots. and then divide them by 2.
Yeah, so
And that
0
works
plus
even
1.
when it's negative, right? When you have negative roots.
Yeah.
When you add them up, you still divide by 2 and you'll get it. Cool.
Yeah. Average. The middle is the average in many cases. There are many
what
different
you-
types of middles, but in this case, we want the average for that middle.
I see what you mean.
Ooh. You know how they taught me mean, median, and mode? The mean comedian sits on the commode.
I don't get it.
It's just, you know, the commode is a toilet.
Yeah. But then,
I don't know. That was just like the
How does
mnemonic
that-
device to remember the 3 words.
oh, just to remember the words, not to remember
Yeah,
what they
it doesn't
do.
tell you
But
what the mean, median, and mode
how
are.
does that connect at all?
Well, comedians, they're always trying to get the majority of the audience to laugh. Anyways,
Right. So, I totally lost what we were doing.
we were trying to find the maximum of this thing, and we found out that 55. What are the axes on this graph?
The axes are our horizontal axis is M and our vertical axis is P.
So 55 is the M value that maximizes this. So I think we can do back sub and get the L value, and we got our 2 values.
Okay, so into L right there. So we got L equals 110 minus 55, our M. And 110 minus 55, 55.
55. Oh, so it's just like the same number. Did we
Cool.
answer the question? What is the
No.
greatest product of 2 positive real numbers? We did not.
We're looking for the product. So the product is 55 times 55, and I'm going to be lazy and write that as squared. And what is 55 squared?
55 squared. 50 times 50 is 2,500.
Okay.
Oh, I like what you're doing. Let's do this. So we got
You said what is it?
2,500 plus 25 on the other side, and then plus 500.
500 from 250 times 2.
Yeah.
And what is that?
That's 3025.
3025.
That like I probably just made every elementary school math teacher cringe
Why?
by saying 3025.
Oh. It's fine.
I got yelled at a lot as a kid because I said 3,025, that kind of thing.
Oh. I don't know.
My
I
math
don't think
teacher.
we had to do that much.
Yeah. Well, you know, every teacher has their weird things. I have plenty of them. Don't worry.
It's the Barnsley education part.
Barnsley education.
All right. So now we answer the question. So we have 3,025 is the greatest product of 2 positive real numbers whose sum is 110. Go Terps.
Go Terps.
All right. Last problem. And this is a doozy.
This is a doozy.
Yeah.
I feel like people don't say this is a doozy often enough. I think it's a good phrase.
Oh, okay. Yeah. So this
Can I
is a
read
doozy.
it?
Yeah, go for it.
The owner of an apple orchard estimates that 24 trees. Sorry. I have to start over. I have to get into my character. The owner of an apple orchard estimates that if 24 trees are planted per acre, then each tree will yield 600 apples per year. For each additional tree planted per acre, the number of apples produced by each tree decreases by 12 per year. How many trees should be planted per acre to obtain the most apples per year?
Wow.
End scene, sorry. I have to get out of that character. I'm a method actor.
All right. So how many trees should be planted to obtain the most apples per year? So the thing we're trying to optimize is the number of apples that we're getting. So how can we figure out what our constraint is, and how do we figure out what our objective function is? I'm kind of at a loss of how to start, Mr. Kirk. What do you think I should do?
Well, let's start let's define our variable. So you want to say like our goal is to optimize apples per year. So let's call that A. All right. That's a good start. Just like getting terms out there. The number of trees is an important thing. So let's call that like T, I guess.
T. Okay, I'm gonna
Yeah.
do little t, and I'm gonna give it the little foot. I'm gonna little the curve so that we don't confuse it with plus.
Nice. And then what else do we care about here? That looks like it's kind of it. All right. I'm still kind of at a loss. Can we just like do a couple of examples?
Yeah.
And like,
can we organize it in a chart?
chart.
Chart.
Whenever Mr. Stein says chart, he goes chart. But he does charts every single day in stats, so you can imagine how that might get annoying.
Yeah.
Chart.
Oh my gosh. I'm so glad I teach in a portable and I don't have to hear that like down the hall.
Chart. Or I'll stop. I won't do
Oh
it
my
anymore.
gosh. So what's on the left of our chart?
Let's put number of trees, and then we could say per acre, but everything's per acre, so
we're just
I'm kind of imagining this problem. I'm imagining one single acre.
Okay.
All right.
And then one single year.
Yeah.
Because we're looking at per year per acre. So if it's in the units in our answer, then we can just kind of ignore it.
I think there's maybe not another. Don't put A there. Don't put A there.
Why?
Do this for me. Put like do like a lowercase a. Let's define a new variable.
Ooh.
Because lowercase a is going to be number of apples per tree. Right? That's a little bit different than the apples per year.
Okay.
Right.
Okay.
So, because like, then give me a third column there.
Ooh. Chart.
I said I wouldn't do it anymore. And now put your capital A. Because if I want to do an example, if I plant 24 trees,
which is what we're given.
And if that's the case, then each tree will yield 600 apples. 600. I like to think that like the more trees you plant, the more nutrients are being sucked up, thus less nutrients per tree, thus less apples per tree. So the more trees you plant, the less apples each tree will yield. You see that when you have a more dense apple orchard, each tree is going to have less apples on it because they're sharing the same amount of nutrients in the soil. So we want to optimize the amount of trees to get the most apples. More trees does not necessarily mean more apples. If you plant 1 billion trees in a tiny little like square,
you're gonna get 0 apples.
You're gonna get 0 apples.
They're all gonna die.
They're not gonna have enough nutrients to sustain life. All right, so if we plant 24 trees and each tree gives us 600 apples, we are gonna get 24 times 600,
which is.
Don't worry about actually calculating it. Does it even say to calculate the number?
Oh.
How many trees should be planted? So just take 24 times 600.
Cool. So can I erase this apples per year?
Yeah.
All right. So what happens if we plant 25 trees per acre?
So each tree is going to give you 12 less. So that's going to be 588 per tree. I'm going to bring out my calculator real quick. Well, let's get those numbers. Let's see what's happening. If I plant more trees, do I get less? So 24 times 600, that's 14,400. If I plant 25 trees, 5, 8. You know what? I guess we are calculating. I'm sorry that I told you to get rid of the column. 14700. Oh, we go up. If you plant more trees, you get more apples. Okay.
Oh, that's good.
Let's do 26.
So what is it? 576?
14976. I just noticed something.
Yes.
The amount of apples that decreased. Does that make sense?
Oh, like second difference?
Yeah. Like from 24 to 25, we gained 300 apples. But from 25 to 26, we gained 276. I think at some point we're going to stop gaining.
Less gains.
What if we add n trees? New variable, we need to define it.
N.
N is number of trees more than 24.
Okay. Per acre.
Per acre, yeah.
So then our little a is 600 minus 12 n?
Mm-hmm.
Okay. And then what is our cap A?
24 plus n times 600 minus 12n.
Whoa.
That is a quadratic.
Boom. Go Terps.
Go Terps.
So what do we do with that quadratic?
Let's optimize it.
Let's optimize. So,
Optimus Prime.
did you see that they made a Gungan in Japan?
I don't know what that is.
Gundam.
What is that?
It's like a giant robot, like the Transformers robots. They made one, but it moves very, very slowly. So they did like a time lapse video of it. So it looks like it's actually moving.
I don't want to spoil any Legend of Korra, but do you remember the end of Legend of Korra? Just say yes or no. This is for the people that remember the end of Legend of Korra.
No.
Season 4, final battles. Anyways. Nope. Let's go. Let's keep going.
All right. So go Terps. So we have this. We have a quadratic, and that's what we're looking to optimize. So if we have 24 plus n times 600 minus 12n, then we have an objective function that is taking into account our all the constraints that we had on what our trees are doing per acre, like how many apples they're producing. So how do we maximize this?
Let's do what we've done. Let's do what we know. Let's look at the roots. Let's do a little tiny sketch graph. And so we got a root of negative 24. And then I think you know what 12 times what gives you 600? Didn't you write that earlier? Maybe you did 500.
Should we factor?
We could do some long division.
Nah, it's okay. I think we can find a GCF. So 600.
So 3 goes into both.
3, okay.
We could do this in increments.
Wait, but isn't 12 times 5 600? 12 times 50.
12 times 5 is 60. So 12 times 50 is 600. 50 is our root.
Oh, wait, yeah. Oh, my gosh. 12, we factored out. And then we have 50 minus n. So we got 50 as a root. And then our parabola is going down, right?
Yeah. You got that negative n times n is negative n squared.
Pardon the rough sketch. And then we got our middle point. What's the middle point from negative 24 to 50?
50 plus negative 24 divided by 2, which is going to be 30. It's going to be 26 divided by 2, 13. 13. So 13 trees maximizes it.
13 is n. 13 is the number of trees more than 24.
37.
So we need the number of trees planted per acre, 24 plus 13. Plus 13, 37. Should we write like units or something on our answer?
Let's do 37 trees per acre. I'm curious how many apples we get.
37 trees per acre. So we
37.
Have 600 minus 12 times 37. No, not 37. It's 13.
13, yeah.
N, right.
12 times 13. 16,428.
16,428.
And if you plant 38 trees.
So if you have 14 trees per acre in addition to the 12.
You get 16,416. So that's when it starts to go back down. It's like a ball.
Negative something. Negative 8. That was a really good sound effect. So what's the actual answer to our question?
I think 37, right? How many trees should be planted per acre to obtain the most apples per year? 37 trees per acre.
37 trees per acre. Boom. Go Terps.
I don't like how acre is spelled.
Acre.
Acre.
I wonder if that's from like Latin or something.
I don't know.
Because you know, like pounds.
LBS.
Because it's Libras, right?
Oh.
But I think that's Latin.
You're teaching me.
I think. I don't know. It'd be interesting to see how, like, if someone explored in a journal how all the units became what they were.
Yeah. The origin of mathematical, or not just mathematical terms, but like just many of the terms that we use in science.
Mm-hmm. Oh, icebreaker. I have an icebreaker question. What's the units you use most often, Mr. Kirk?
Kilometers, and it drives people insane. My Google Maps is in kilometers. As you said the question, I knew the answer immediately. Kilometers. Like you even see when I'm doing my my running, it's in kilometers. I got to 100%.
Oh, congratulations!
Miles. I got to 160.9 kilometers.
Good job, Mr. Kirk.
How are you doing on your plank?
So I reached a wall where I could no longer like go for more time doing the same kind of plank, and so I changed strategies. So now I'm seeing which kinds of planks I can do for the duration of 5 minutes, and then I'm gonna increase the intensity of those rather than going for like longer time with like a full like elbow plank.
So you're allowed to switch your position during the 5 minutes, is what I'm hearing?
I'm trying to see, like, so now I can do a high plank on my knees for 5 minutes. So then next I'm thinking that I would do like a low plank or like maybe halfway through switch.
So rather than altering the length of the plank, you are slowly making the type of plank more difficult until you get to the standard plank.
For 5 minutes.
For 5 minutes. Wait, yeah. Answer the question though. What unit do you use?
I use grams because when making coffee and stuff, there's a lot of grams happening, and I don't really measure most of the time when I'm cooking other things. I just don't measure stuff.
Oh my God. I am obsessed with grams. Every single thing I do, when I cook, when I bake, when I make smoothies, I'm measuring in grams. Everything I make is to a T the same as it was the previous time.
That's interesting.
I'm 100% on board with you with grams. I actually think I use grams more than kilometers now that you've reminded me. I have a really awesome, high quality scale.
Like a kitchen scale?
Yeah. Mary Kay, can you grab the scale real quick? I love my scale. And it's actually when I go to weddings, I always buy this scale for the people getting married.
Oh, wow. That looks like a chemistry set kind of scale.
This is like legit. And it can handle up to like 50 pounds, which is like a big deal to me because I'm constantly weighing a tremendous amount of flour when I make large loaves.
But you have a 50-pound bag of flour or like 25-pound bag of flour? We
got grams right there.
It's
not going to focus. All right. But yes, you have, you know, that meme changed my mind?
Yes.
Yes. You've changed my mind.
Oh, bet.
Although you cannot change my mind about using imperial over metric. You can't change my mind about that.
That's fine. I don't care that much.
All right, I think we've closed out. Let's do it the normal way, but
all right.